This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That we know in order to work out what the initial forward going voltage wave is going to be is we're going to use a voltage divider. But in this particular case, what we need to do is only focus on, we've got the generator impedance and the characteristic impedance of a line. That's the only thing that happens when we've got a transmission line and we just, on that very, very first instance, when we switch that transmission line in, the wave hasn't actually gone down to the load, so it doesn't actually know what's connected there, right? And that's distinct to your first year steady state or analysis where you did your DC and you said, well, what I'm going to do is I'm going to work out RG, work out what the load is, and that's how I'm going to work out the current on that and the voltage across that resistor or across that load. Here, what we're saying is there's actually, the signal travels with a finite speed, and it's the speed of light divided by the phase impedance or the phase velocity in that actual medium is how long, and the distance, it dictates how long it actually takes for that disturbance to actually hit that load impedance, and then actually understand, for it to then change the boundary conditions in order to be able to deal with, that there is that impedance at that location. And what we did is we went through this analysis, and what we said was, this positive going wave, it's going to hit the load. Then something interesting happens when we actually hit the load, which is initially what happened was there was a particular voltage here, which was dictated by the voltage divider between the characteristic impedance in the line and the generating impedance. When it actually hits the load, all of a sudden we realise, or the wave realises, that it doesn't meet the boundary condition. And under those circumstances, once it realises that it doesn't hit the boundary condition, or it says, under these circumstances that the physics isn't being met, right? So therefore, all of a sudden, in order for the physics to be met and Ohm's law to be met, what happens is we quickly realise that there has to be a reflected wave at that particular location in order to be able to meet those boundary conditions. And there, what we did is we went through and satisfied, these boundary conditions in order to work out what essentially rewritten the Ohm's law in terms of these boundary conditions. In this particular notes, I've made the correct definition of gamma, which is V minus and V plus. Thank you for pointing out that I'd made a mistake a few slides ago. I've made V plus and V minus, which is incorrect. It's V minus and V plus. So thank you for pointing that out. All right, good. And we've also got I minus and I plus is equal to minus gamma. And essentially what we've calculated, what we've determined there is we've got now a positive and negative going wave. The same situation occurs when we hit the discontinuity at the generator, and we get another reflected wave depending on the characteristic impedance of the line and the characteristic impedance of the generator. And the source impedance of the generator. Then we went through an example problem, and in this particular example problem, what we did was essentially said, well, we've got a source generator with 40 ohms, 100 volts, 60 ohm characteristic impedance line, 100 ohm load impedance, and we went through and did the calculation. All right, and in this particular case, it was relatively simple to do, but your dumb lecturer made a mistake, right? So the bounce diagrams are correct. The only thing is I couldn't count by halves here, and what I did was this should have been at 3.5, I've actually put it at 5.5. So essentially what happens is we've got the voltage wave, it goes from the source to the generator, it hits the source to the load, I apologise for that, hits the load, works out that it doesn't meet the boundary conditions, we get a reflected wave. Since the the voltage of the generator remains there and it's not transient, what happens is we get the addition of the 60 plus 20 volts. That's why we get 80 volts. Now, we've also shown an example where we put a pulse, and at the time when the pulse dies, there is no longer that 60 volts there, right? And under those circumstances, you've got to make sure you're adding the right two components. Okay? So we went through, we worked out the bounce diagram, and we worked out what the impedance is going to be at the source. We worked out what the impedance is going to be somewhere in between, and that's where I've made a mistake. This should have been at 3 on 2 rather than 5 on 2. I just made a mistake. For whatever reason, I looked at 5 and 2 and thought it was 3 on 2. Dumb, I know, I apologise. So that's been fixed, so that should be, you've got a wave going there and then that goes down later on. And we've also got the impedance, or what the voltage is at the load. Okay. Then I went through and said, hey, we're going to make this a little bit more difficult. And essentially all I did was say, well, instead of actually transmitting a constant voltage, what we're going to assume is that this generator is actually generating a pulse. That's a one-off pulse, right? And we said that the width of that pulse, or the duration of that pulse, is 1 microsecond. In order to complicate the situation much more, I also made that the time that it takes for the pulse to travel along this length of line was 1 microseconds, right? I could have made that much larger and made it a little bit easier, but I just wanted to illustrate a point. And essentially what I did was show, we've got we've got the standard bounce diagram, but I also added another dimension here to indicate time. All right, so therefore we've got the 60 volts, the line, it's traveling, the signal before it finishes, there's a signal still on there until it hits completely the other end. So that's why you got 60, you still get situations where you've got 60, you've got 80, but when you hit here, the 60 volts from the pulse generator, or the positive going voltage has dissipated. So now you've only got the negative going voltage, or the negative going voltage wave, which is 20 volts. And this is where all this is coming from, right? So what I wanted to do is, illustrate that if you've got a transient, it becomes a little bit more complex. And essentially what I've done is I've used those pulse bounce diagrams in order to indicate to you what the voltage is going to be at the generator, at the load, and somewhere in between. Okay. Now, I said, well, I wanted to make it even a little bit more complicated, and I probably confused myself while I was doing that. But essentially, what I wanted to illustrate to you was a particular example where you now have some initial conditions on those transmission lines. Okay? So there's no reason why these transmission lines need to be at quiescent conditions, meaning no voltage, no current, right? And the reason why I was doing this was also partly because I was thinking of an example of generating an EM pulse. Who knows what an EM pulse is? Electromagnetic pulse. It's not on here. Let me say something else. So you've probably seen in a whole bunch of maybe even movies or even, whatever, where if you're generating a big pulse, electromagnetic pulse, all of a sudden it can actually destroy electronics, it can actually switch things off, it can do a whole bunch of things. And essentially what I was doing was showing to you, ways in which you can do certain of these tricks and use these transmission lines in order to be able to generate these kind of pulses. Right? It's a lot of fun for people like me to play around with these kind of things, but I thought maybe you'd be excited also. And that's the reason. So one of the things that you can do, but don't do it because you'll get into big trouble, is you can actually have a generator, and you can think of this generator connected to a very large impedance. We call this R, and let's say this is 10K or something, 10 kilo ohms, right? Now, here I'm going to say this is 1,000 or 10,000 volts, and it's not very difficult to generate those kind of voltages. This is an example. It's not examinable, but this is just to make you feel excited to be here at this course and say, hey, I'm actually learning something really cool. Stan's really teaching me something really cool. And, you know, in its, it's called a Craycroft Walton generator. So which essentially what you do is you connect a collection of resistors and capacitors in a particular way. Sorry, resistors, capacitors and diodes in a particular way. And it's actually diodes and capacitors in a particular way, so that you actually get voltage multiplication. So what you do is you pump it with a small sinusoidal signal, and depending, it's something like this. It's your diode, capacitor, diode. Anyway, and it just multiplies the signal up. So you can actually look at it. It's a So you can put, you know, 10 volts in or 100 volts in, and you can get 10,000 volts out, right? Now, you connect it up with a large impedance to a transmission line. Let's assume this is Z0, and then you connect this up to an antenna, which has got, hopefully this is all being recorded. I guess hopefully I don't get myself into trouble. So you connect it up to a 50 ohm, and let's say this is 50 ohms. All right, so you charge this line, you leave it for a second, you charge it up, it goes to 10, so this line is 10,000 volts, essentially, or 10 kV. So you've got to choose the right transmission line and the right coaxial cable and whatever. And then what you do is at some time, you close that switch, right? So what happens? Well, depending on, because this is very high impedance, it's almost, you can almost approximate it as an open circuit. What happens is the length of this transmission line, the voltage across this transmission line goes through the impedance, depending on that length or the time it takes for the wave to go from one end of the transmission line to the other. So, you know, if you can think of it, you can actually make a pulse of tens of picoseconds, right? Tens of picoseconds, and if you think about it, if you've got 10 kV here over 50 ohms, what's the current going to be? 200 amps. So you're getting 200 amps across this line over 10 picoseconds. So you've got this very sharp pulse that's gone through, right? And then you can actually see, you know, if you've got a very sharp pulse, you can actually work out what the frequency components is and whatever. So you've actually generated a huge pulse, lots of energy across this antenna, and it's radiated everywhere. So that was part of a reason that you use these kind of things to build these kind of structures, because usually trying to switch 200 amps in 10 picoseconds is bloody hard, right? No matter what IGFETs or IGBTs that you try to use, you can't do it. It's really tough, right? But you can use this trick, this transmission line that you've charged up, whack, connect it up. This is only, it's got energy only for a finite amount of time, and because of its length, it's only got a finite duration. It does a really nice little pulse for you. And you can charge it up in a second, bang again, and bang again. And you can stop everyone watching TV or listening to, doing WeChat or whatever. So, that was the reason, right? But you do it for other things also. You also do this if you want to power a laser. You know, some lasers you need to, you know, some chemical lasers you need to have a very sharp, high pulse in order to get them to actually, you know, you stimulate the radiation out of that laser. This is just showing you the technique to do it. Okay. So we had these lines with initial conditions, and all I was saying is, hey guys, what we're doing here is, you know, the line can be charged. right? It doesn't have to be at 0 voltage, right? And all I've done here is I've written the voltage across that line in terms of the positive and negative going voltage waves, and of course I've done the same in terms of the positive and negative going current waves. And I just reminded you of the relationship of, the characteristic impedance versus the ratio of the positive and negative going currents and voltage, and for both situations, and rewritten what the positive and negative going voltage is in terms of the total voltage on the line, characteristic impedance, and the total current on the line. And then what I did was all I wanted to say to you is, hey, I've got this charged line, and for whatever reason, right, you can say to me, why this? I just said, this is the given the voltage on this line. There's no reason why it has to be this, I just chose it, right, as an example. And also, likewise what I did, I said this is the current on the line. Great. And what I did was then worked out the mathematical relationship for this, and then used the formula in the previous slide in order to calculate the positive and negative, the positive going voltage wave, and the positive going voltage wave and the negative going voltage wave. And essentially all I did here was to say, well, for that particular voltage characteristic that I had, the positive going voltage on the line from 0 to L on 2 starts at 25, goes to 50, and then from L on 2 to L, it has this relation, goes from 50 to 0, based on this initial distribution of the total voltage. Right? And I also said that the negative going voltage is this. I calculated it, I shouldn't say said that it was this. Okay. Then I said, well, hey, let's look at this and what happens once we close that switch. So we know that this voltage component, of this voltage characteristic, is now, once I close the switch, is going to be moving forward in time, right? So at time 0, the load's going to see 0 volts. At time corresponding to L on 2, this is going to move to the load, right? And also, what we're going to have is this point C is going to be somewhere in the middle here, or in the middle of the line. Now, likewise, one of the things that we've got is we've got the negative going wave, right? And all I said is, because we've got the negative going wave, it's going to also hit the discontinuity in this transmission line, because remember it was an open circuit. And we know for an open circuit, gamma is a positive one. And essentially all I said is, as this hits, what we're now going to get is we're going to get this component is now going to start moving, in the opposite direction. So what we're going to have is this is going to be essentially, mirrored about this point. And then I said, well, if we've got that, and then we've also got this component, which is now moved to this point, the C's moved into this point. Now, what we've got is C is going to be here. Now we've got this negative going component, which is flipped and moving, is going to be the continuation. And that's where the resulting waveform comes from. That's it. Right? Okay. Now, what I was going to do is, because I had a few of you ask me some questions, and I didn't know if you completely understood it, I'm going to give you another example. All right, I've gone through and worked out another example. And I've got a turn on transient, and then I'll do a turn off transient. Okay? This you're all very comfortable with, right? It's at 0, I'm going to turn it on. I've got the generator goes essentially from 0 to 4 volts. And what we said is, when we work out what the initial voltage going wave, I'm not drawing it in terms of balance diagrams, I'm drawing it in terms of the voltage waves on the line, just to help you conceptually understand this. We've got 50 and 50, so therefore the voltage at this point is going to be half, so it's 2 volts. So as time goes past, at at a point halfway between, if we're looking at a time L on 2V, what we're going to see is if we were at that location, we've got a positive going voltage wave that's just about to hit us, right? The negative going voltage wave is 0 because nothing's been reflected as yet, right? This switch is closed, there's nothing that's been reflected back as yet. And the total voltage is V plus V minus. So this is what the total voltage on the line looks like. I said, what happens now if we're looking at a time 3L on 2? Well, at that time, at time equals L, we know that the line is actually, the disturbance has actually hit the load. It's now beginning to travel backwards, so therefore that's where we've got this component, because we also know what the reflection coefficient is. We've been told it's gamma L equals to 1/2, so if that's 2 volts, we have a negative going coefficient, it's going to be 1/2. And if we're summing the two components, we've got the total voltage on this segment of line is 3 volts. The disturbance, the negative going disturbance hasn't hit yet, so in this location it's at 2 volts. Okay. Now, we've got that situation. Then what I've said is, at some time far into the future, what we're going to have is, we're going to get steady state conditions, so therefore what we're going to have is the positive going wave is going to be 2 volts, the negative going wave is going to be 1 volt, the total voltage on the line is going to be 3 volts. Just to convince ourselves, we know if we do Ohm's law, if we had 4 volts from the generator, the total impedance is 200 ohms, 150 ohm load, 50 ohm source impedance. So therefore we know that the total current is going to be 1/50th of an amp. 1/50th of an amp. Let's convince ourselves that that's correct. Also, based on these equations, we know that V plus on I plus is Z0, and we also know that V minus on I minus equals minus Z0. So we do the calculation. The positive going wave is 2/50. The negative going current wave is minus 1/50. When we sum them up, it's 1/50. The two match. Thank God, right? Because otherwise, if they didn't match, we would have lots of problems, right? So that's all. Well, that's all I've done. Now, let's go through and look at what happens. So we've got the steady state equations. So what I'm going to do is use this to do what I did previously. We've got a steady state solution. Now we want to work out what's happening and what happens if I open or close the line. So in steady state, I replug all these values in, and I get the values, and you can do that yourself. That, if I had V0, I0, I can actually get the right V plus and I plus, V plus, V minus. Everything's great. Now, suppose we've got this situation, and what I'm going to do is, at time equals 0, I'm going to open the switch. Right? That's all I'm saying. I'm opening the switch. And essentially, here what I'm showing is the voltage at the source, is 4 volts, then it dies to 0. Let's do our transient analysis. We know at time equals 0, this is the situation. As, at time L equals on 2 on V, well, what happens is this voltage goes to 0, so therefore wherever it was 2 volts, it's gone to 0 volts. But this is only as far as this disturbance has moved in that time. So it's 0 here, 2 volts for the positive going wave. Not enough times occurred for the negative going wave to be modified, so that remains at 1. And our disturbance, or the transient on the line, is 3 volts in this section, 1 volt in that section. What happens when time equals 3 lambda on 2V? Well, on that time, there's been enough time for this transient, or for the to propagate all the way to the end of a line. What's happening, and it's beginning to move in this direction. So the positive going wave's gone to 0. The negative going wave, this section's gone to 0, but this section has not as yet. So therefore, we get this relationship. And again, the sum of the two voltages, in order to get the total voltage on the line, gives us the gives us the resulting voltages. And then at some time greater than 2L on V, what happens is the line's died and it's completely in a quiescent state. All right? Exciting? All right, cool. All right, I'll put those up on the on LMS, but essentially what I'm showing you is how to do some bounce diagrams, and especially when you've got non-quiescent conditions. All right, now to this part of the lecture, what I was going to talk about is some special kinds of waveguides, right? And particularly, I was going to talk about, we've talked about coaxial waveguides, we've talked about two parallel lines, and we talked about two parallel plates. All right, that was in the past. Today, what we're going to talk about is strip lines and microstrips. Right. Who's seen a strip line before? Okay, yep. Who's seen a microstrip before? Same people? All right. Coplanar waveguide? Coplanar waveguide. I'm not going to talk about them today, but it's essentially three lines where you've got the center line being your signal line and two lines on either side of it being your ground. All right. But what we're going to do today is only talk about strip lines and microstrips. And essentially, for everyone's benefit, you need to know, when somebody's saying this is a strip line or this is a microstrip, you need to know what it is, right? You can't be finishing electrical engineering and not knowing what a strip line or a microstrip is. So essentially, for everyone's benefit, a strip line is a planar transmission line. And essentially, the reason why I'm teaching you about microstrips and strip lines is when you're designing waveguides or ways in order to transfer energy across a PCB board or a chip, there's usually three techniques that you use. You either use a microstrip line, a strip line, or a coplanar waveguide. So, but I'm not going to talk about a coplanar waveguide today. We're only going to talk about those two. That's the reason why I'm telling you. If you're designing waveguides in order with a known impedance, they're the two techniques that you usually use, right? And you just have to know about them. Now, why am I talking about coaxial cables? Well, other than we've done it in the past, you don't make coaxial cables. You just go buy a coaxial cable, right? Whereas if you're actually building a PCB board, you need to be able to, depending on it's the distance between layers, the thickness of the metals, the dielectric constant, the loss tangents. All that has to come into it when you're actually designing it. And we'll go through this today. So essentially, the way that you create a strip line is essentially you've got a ground plane on the top and the bottom, and then you've got a conductor in the middle, right? And it's symmetrical, right? And the benefit of a strip line is that it can support TEM transmission, which is transverse electromagnetic modes. Now, it can also support other types of modes, but usually what you do is if the thickness is less than a quarter of a wavelength, or you actually add shorting pins or ground vias between the ground planes, you can actually stop like transverse electric or transverse magnetic only modes from propagating. All right, forget about that. The thing that's important for you all is to say, hey, I've got a strip line. A strip line is created on a PCB board where I've got a little bit of ground plane on the bottom. And ground plane doesn't have to be infinitely large. It can be just a small piece of metal, right? And in the middle, I put my conductor, which I'm actually using to transfer my signal. And on the top, it's symmetrical in terms of the distance between the top and the bottom of this, whatever. I've got another ground plane. Okay. Now, it wouldn't come as any surprise to anyone. It shouldn't come to any surprise to anyone because it's symmetrical that the phase velocity in this particular medium is just the speed of light divided by the dielectric constant, the square root of the dielectric constant. Right? And we've always talked about this where we've said the speed of light is 1 on the square root of mu naught E naught. And then we've said if we've got a particular medium, the speed of light or the speed of an electron in that medium is 1 on the square root of the total permeability times the total permittivity. Or we've written it as, you know, the total permittivity is ER times E naught, mu R equals mu total equals mu R times mu naught. Anyway, this is the phase velocity. So therefore, if you want to work out how long or what the speed of light is in your particular medium, you always use this formula, provided it's not a magnetic material. And remember, these PCB boards are usually dielectric, and usually they're some kind of woven glass, like FR4 is a woven glass, or a woven fiberglass. So you got, like, if you've got your velocity, your phase velocity, you also know that there's also a propagation constant which relates essentially, which is in vacuum it's just K, in a medium with a permittivity not equal to that of free space. It also tells you that the wavelength changes, right? So therefore, rather than having 2 pi on L, you've got now 2 pi on L multiplied by square root of ER, because all of a sudden you've got the wavelength has changed in that medium. And likewise, you've got the characteristic impedance of a transmission line. We know that the characteristic impedance for a lossless transmission line is L on inductance on the capacitance. Now, usually, to calculate the characteristic impedance of these lines, it's really, really tough, right? You know, the calculations, there's a whole bunch of Bessel functions, whatever, etc., etc., etc. Now, what I'm doing here is giving you formulae that people have determined, which essentially what they've done is fitted what the impedance is on this line, so that you can actually use that formula in order to calculate the impedance. And what it says essentially is that the impedance is 30 pi on the square root of the square root of the dielectric constant, the thickness between the 2 ground planes, and it's assuming here that the thickness of the conductor itself is not particularly thick in comparison to the distance. And usually, when you think about it, like, and I'll show you a data sheet, when you're looking at the thickness of the conductors or the routing layers on the PCB board, they're usually between 2 microns to 70 micron, right? The actual metal, the thickness of the copper, whereas the dielectric is probably anywhere from a couple of millimeters up to 70 millimeters. And we'll go through some data sheets and we'll have a look at it. So we've got the characteristic, formula for the characteristic impedance in terms of the dielectric constant of that material, the thickness between the 2 ground planes, assuming that it is symmetric, and something called the effective width, right? And essentially, what it says is that this effective width is the real width divided by b, which is the distance between the 2 ground planes, and depending on the ratio of the width to the thickness, we have to choose the appropriate formulae. Can someone check that I haven't made, I'm trying to think if I've got this the wrong, these inequalities the right way around. If someone can just check, that'll be good. Or what I'll do is I'll also check. But anyway, what it says is depending on the ratio of the width to the total thickness of the dielectric, between the ground planes, you use either one of the 2 formulae. Right? If W on B is greater than 0.35, you can approximate WE on B is the same as W on the real W on B. If you're thinner, which I think probably I do have it correct, what you need to do is you've got to subtract minus 0.35 divided by W on B all squared. Now, just to reiterate, these are formulae that people have fitted, right? there's no real physics behind it. Okay, so don't try to derive it. Okay? That's what's important. Don't try to derive it. What people have done is essentially have built a ton of these transmission lines, or essentially have simulated a ton of these transmission lines and have done some fitting. They've said, like, remember when you don't want an equation, or a particular equation, you say, let's assume the data fits AX plus BX, and let's find out A and B so that it fits the data. That's what's been done here. So there's no real physical intuition. So don't try to derive it. You just have to say, somebody gave me this formula. They're smart enough that that it's correct, and that I'm going to use it. Right? Unlike a lot of the other formulae where there's a physical reason and it can be easily derived. In these ones, it's actually just fitted. Okay, and that's important. So don't sit there for. I know some of you like deriving all the formulae that I put on the slides. Don't do it for this one. Okay. And likewise, what we do is we determine the conductor loss. And there's a complex formula here for the conductor loss, and in terms of A and beta, A and B, and we use different formulae depending on if the square root of the permittivity times the characteristic impedance that we're trying to, the characteristic impedance of a line is less than 120 or greater than 120. So essentially what you do is, when you're doing these calculations, you'll assume that it's 1, you'll calculate it, and then what you'll do is you'll be either, hey, I'm lucky and it does meet all my conditions, or, oh crap, I chose the wrong one, now I've got to go and calculate the next one because it has to be the other one. Right? You got no choice, right? That's how you got to do it. Right? So here, if I said to you make a 60 or 70 ohm line, what you would do is say, all right, 60 ohms on FR4, it's greater than 120, so therefore you'd say, oh, I'm going to use this formula, right? And therefore that's where that's how I'd calculate my conductor loss, right? And likewise, we've got conductor loss. We've also got the loss tangent for a particular material, and the dielectric loss is K, right, which is the wave number times the loss tangent divided by 2. So let's go through a quick example, all right? And what I'll do is, who's actually seen a data sheet for a how do you call it, for a dielectric material? Okay, so this is a data sheet for a material called FR408, which is a high performance FR4. Does everyone know what FR4 is? No? You know what a PCB board is, right? Okay, the green material that makes the fiberglass, that's FR4. That's what you're using to make your materials. Now you can use PCBs, you can actually use different types of materials, like depending on the performance that you require. FR4 is usually good to a few gigahertz. But if somebody gave you a material, usually what you need to say, because there might be cost constraints or performance constraints or some other constraint, what usually you do is you grab the data sheet, right? Because a particular manufacturer, and this is what's important, like for example, certain manufacturers, they use different quality of FR4. So even though you might say manufacturer A is giving me FR4 and manufacturer B is giving me FR4, they're not necessarily the same FR4, right? So you've got to make sure that they're the same loss tangents, a whole bunch of things. But anyway, so this is the data sheet, and usually what they do is they give you, what temperature can it withstand, the dielectric constant, and the loss tangent. But usually that's defined at a all these are defined at a particular frequency, and what you will see here is the permittivity is frequency dependent, right? So at 100 meg it's 3.69, At 10 gig, it's 3.65. It's not too bad in this particular case, but usually it can go from 3.69 to 2, right? And the loss tangent here, you can see that it goes from 0.0094 to 0.0125, which again, it's not too bad. But certain other dielectric FR4 materials, this can be much, much larger. It can go from 0.094 at 100 meg to 10 or 100 times that. This is given. This is a data sheet. There's nothing to the right. You just look at it, right? And this helps you decide what the characteristic properties of that particular piece of material that you're going to be using as to manufacture your PCB board, how it's going to perform, or how it's going to perform when you send them the Gerber files in order for that manufacturer to manufacture your PCB. Okay? That's all I was trying to highlight. And for here, I'm just giving you an example. Someone says to you, hey, and it might be an exam question, I want you to build me a 50 ohm copper strip line, right? And the thickness between layers, or the layer thickness, is 0.16 centimeters. It's quite relatively thick, but usually what happens is you can actually see that there are only certain thicknesses. This is a bad data sheet, but usually there's only certain thicknesses of dielectric material that you can buy. You can't arbitrarily say, I want 1.7432 thickness of dielectric material. There's only certain thicknesses, right, that people manufacture. So usually what has to happen is you've got to, you're given a thickness, you're given a dielectric constant, you're given a loss tangent, you're given a desired operating frequency, and usually you're given a copper thickness. Usually the copper thickness, however, just for a laugh, is usually given in ounces, and it's ounces per square meter, right? So therefore that relates into thickness in micrometers. And this is just so that you know how to read these data sheets. And what I'm asking you to do is, design this strip line, and I also want you to calculate the loss in dB per wavelength. Okay? As an example. Okay, so usually, okay. So the first thing we want to do is, we said we want 50 ohms. We rewrite that in terms of the x, where x is the relative potential thickness. So we go, essentially that's 30 pi square root of the square root of dielectric material Z minus 4.1. So I've only just transposed that. And we use this to calculate W and B. So we've calculated X in this particular case, right? And I've calculated X. X is less than 0.3, is equal to 0.830. And because also the characteristic impedance times the square root of ER is less than 120 in this particular case, I can actually use W on B. X is equal to W on B. I don't have to make that correction. I know what the thickness between the two ground planes is. We said that the thickness of the material was 0.16 millimeters or 0.16 centimeters. So the width is actually 0.266 centimeters. Now here, you just got to be a little bit careful that I'm actually using here all centimeters and millimeters. If I'm plugging it into certain things, you just got to make sure that I'm dimensionally correct, right? So just be a little bit careful there. And then what I'm saying is, in order to achieve the desired 50 ohms for the material with the characteristics that we've just looked at, I need the width of the center strip to be 0.266 centimeters. Great. Now I want to work out what my total loss is, and we've said that the total loss is the dielectric loss plus the conductor loss. We had formulae to calculate what the dielectric loss was, which was K loss tangent on 2, which is essentially 2 pi K in that material, which is 2 pi F on C, which is lambda, times the square root of the dielectric of that material, times the loss tangent. So it's 0.155 nepers per meter. The loss, the conductor loss, we had the formula for the conductor loss, if you remember, here. And we had, depending on which arm we were, it was the dielectric, if the square root of the electric constant and Z0 was less than minus 120 or greater than 120. In this particular case, we're less than 120, so we can actually use, we have to use the top equation. We substitute all the values in, and what we do is we get the loss, for the conductor loss, is 0.122 nepers per meter. Right? Now, why is this all important? If you're designing this, right, we said that we've got some degrees of freedom, right? And some of the degrees of freedom were, we can actually choose the thickness of the copper, and we can also choose potentially that gives us 1 degree of freedom. So therefore, if we wanted to make that loss a little bit less, we can actually choose that, or we can actually choose a different material. In this particular case, I've told you you've got to use this material, but generally what you can do is, if you wanted very high loss, very low loss, high fidelity, what you would do is you could choose either thicker conductors and/or different dielectric material. Anyway, I've got the total now, total loss in nepers per meter in terms of dielectric constant and conductor loss. I summed the two, but I've asked you to work it out in dBs per meter rather than nepers per meter. And we know that nepers was e to the A, right? Was e times to the alpha propagation constant, right? So therefore, to convert it into dB, it's minus 20 log e to the power of A, which is just minus 20A. But here I've got it in, how do you call it, natural log. If I'm converting from natural log to log base 10, I've got to divide it by log e of 10. And if you do the calculation, it turns out to be, you're getting about 2.41 decibels per meter loss. And at 10 gigahertz, a wavelength is about 2 centimeters, so therefore you're getting, if you do the calculation, you can actually show that it's 0.05 dB per wavelength. All right? Exciting? You should now be able to design strip lines. So you know what a strip line is. If someone gave you a material, you can actually design it, right? Now let's quickly go through. Ooh, have I gone over? No. Good. I was worried for a second. The other type of line or waveguide that we need to worry about, or we should be very familiar with, was a microstrip line. And essentially, a microstrip line is a waveguide which has a ground plane. It's got a dielectric slab, which is just the dielectric material, and a conductor on the top of it, right? And the reason why we do that is, ideally, if we wanted high performance, we would put it in between the layers, right? And we'd put 2 ground planes, and we'd get nice TEM propagation. But sometimes you want stuff on the top surface, right? You want to connect to an antenna that you put on the PCB board or whatever. That gives you that extra degree of flexibility. All right. Now, as you can see, a microstrip is not symmetrical like a microstrip is not symmetrical like a strip line, right? And if you look at this, and if we're looking at both the electric and magnetic field, we can see out here is air with a relative dielectric constant of the ER equals 1, and here we've got some other material which has got a different dielectric constant which is not equal to 1. So therefore, we know the strength of the electric field in a dielectric material greater than 1 is stronger or less stronger than the one that's in there. So if we had dielectric material of ER of 2 versus a versus air, which one has the more electric field? Stronger electric field. And why do you make capacitors? I mean, just think of it this way. Why do I make capacitors with a dielectric in it? So I can have, I get a larger field and so therefore the electric field is higher in here, right? And this creates an asymmetry, right? The magnetic field is symmetrical because there's no magnetic material or ferromagnetic material, but there's a difference in the electric field lines and effective field strength between the top and the bottom, or the top, which is in air, versus what is actually happening in the dielectric slab, which this transmission line lays upon. Right? So therefore, there's an asymmetry in this particular situation. Yes?
So let's say we use this in a PCB or something. Isn't it dangerous to just let the electric field go over the PCB rather than just being condensed?
But sometimes you don't have a choice. Sometimes you don't have a choice. You might need to connect to something, and sometimes it's not necessarily dangerous, but it's not ideal. But sometimes you've only got one layer, the top layer that you want to route on, or your manager says, no, I want this to be 50 cents. I don't care. Yes, you'll get worse performance, but I only want a 2-layer PCB board, right? And you've got no choice, right? You're going to go, well, I want a 50 ohm line. What am I going to do? Well, I'm going to do this. I can't do a strip line. Maybe I can do a micro strip. Under those circumstances, you'll probably go for a coplanar waveguide. But anyway, but there's issues with transitions and all the like. But usually, this is just one of the things it's one of the hands that you're dealt with, and you've got to just play it and see where you end up. Now, as you can imagine, right, because it's not symmetrical, it's not pure TEM propagation in this microstrip line, right? Now, but we can play some tricks and we can make it look, because usually what you've got is you either got TM or TE, transverse magnetic or transverse electric field waves propagating in this. You don't have transverse electromagnetic waves propagating in this medium. But notwithstanding that, you can still have some approximations which allow you which allow you to do the analysis. So the phase velocity is just the speed of light divided by essentially what I refer to as the effective dielectric constant, right? And here, why am I discussing or introducing this concept of effective dielectric constant? How is this different to a strip line? Strip line, you've got top and bottom, I've got the same dielectric constant, right? Here, I've got a dielectric constant, a material with one dielectric constant, and I've got a material with a different dielectric constant, or air, on the top, right? So I want to have somewhat similar analysis, but in order to make my life easier, what I do is I try to determine this concept of effective dielectric constant in order to simplify my life. So let's do the following. It's almost 2 o'clock, so I'm supposed to finish. What I'll do, let's do this in the next lecture, right? So therefore, it gives you a little bit of time to actually look at it. I'll put it on the stack. I'll put it online on LMS. But what would be very useful is to look at strip lines. Yes, it is in Poser, so you can actually look at that and look at the design of various strip lines. But I think this is very interesting stuff because it's now you're beginning to have developed enough machinery and enough knowledge to actually start building some transmission lines and start doing some cool stuff with transmission lines, which are important in distributing clocks and signals and high frequency signals across PCB boards and the like. All right, cool. All right, excellent. Enjoy your weekend, which you'll spend no doubt studying high-speed electronics. Quantum switches. lock it.
Here, you're right there. Just